Okay, so today we're going to be talking about the negative lambda case that everyone's been asking about for the previous two lectures. So finally you get your wish. So let's start by thinking about just ADS Schwarzschild, saying 4 dimensions. So if we look at null geodesics of ADS Schwarzschild, then you can reduce the equation of motion down to this this equation here, where you can see the motion is described by an effective potential in the way that we're all familiar with. So h here is the angular momentum parameter of the geodesic. E is its energy. This is the mass of the black hole. This is the ADS length. Okay, so that's the equation for null geodesics. And if we dot is a derivative of this F1 parameter derivative. Yeah. So the effective potential looks like this. So you see it's got this maximum at r equals 3m. So a null geodesic sitting here is sitting on the photon sphere in the same way as for an asymptotically flat Schwarzschild black hole. But the interesting geodesics here are things like this, which come in from infinity, bounce off the potential, and then head back out. So they bounce off at some radius r0, which is determined by the energy.
This is without any angular momentum?
No, this is with angular momentum. So h is the angular momentum. If h is 0, the potential is absent.
The height of the potential is controlled by the angular momentum.
The height will depend on the angular momentum, yeah, but the location doesn't.
Right.
And in fact, it doesn't depend on the cosmological constant either, which is kind of amusing. That's because lambda just gives us L just enters as a constant term in it. So on a Penrose diagram, what do these null geodesics look like? Well, they're geodesics which come in from infinity, bounce off this potential at some radius, and then go back out to infinity.
And between one infinity and the other, how much angle have they covered?
That will depend on the angular momentum. So.
But it's not some integer. Is it closed off?
It's no, because this is a continuous parameter.
Okay.
Well, I haven't thought about that question,
Okay.
but it might be. Would it be infinitely many orbits? No, probably not. Anyway, so that's what they look like. They come in from infinity, bounce off, and go back out. But the interesting thing about this is it means that there are null geodesics in Schwarzschild ADS which are kind of trapped near infinity. So some geodesics are trapped, and in fact, so trapping is basically the idea that null geodesics stay in a bounded region of space. So we're familiar with the idea that these geodesics are trapped, the ones sitting at the maximum, but that's unstable trapping. If you perturb these geodesics, they fall into the black hole or they escape to infinity. On the other hand, this is stable trapping. Okay, if we perturb one of these geodesics, it stays nearby.
And suppose I make this massive for a moment.
Yeah.
Instead of going to infinity, we would have turned around somewhere nearer to the boundary.
Yeah, well, they could be actual bound orbits in the massive
like
case. Yeah, so just like a planet orbiting the black hole.
Okay. For massive particles, you could have shooting particles from infinity because it's an infinitely confining potential for massive particles.
Yeah. So massive particles won't reach infinity.
Right. So it would just be like an ellipse.
Yeah, exactly. Good. So the same is true if you look at more general black holes. So if you look at Kerr ADS, or you do this in more than 4 dimensions, it's qualitatively the same. So what this means is that when you have stable trapping of null geodesics like that, you can imagine just, if you now look at a massless field, you could imagine...
Could I ask in flat space,
yeah.
R equals wherever the photon sphere still exists?
R equals 3m, yeah.
But that continues to be unstable in flat space?
Yeah,
yes.
Yeah. So flat, yeah.
So there are no stable photon orbits?
Not in flat space.
Okay.
No. The importance of this for what we're interested in is that if we now look at fields, massless fields, then you could imagine constructing a massless field localized around one of these null geodesics as a wave packet. And so this stable trapping phenomenon means that this wave packet will decay very, very slowly. So this implies slow decay of massless fields. Outside the black hole. And you can see this if you look at quasi-normal modes of the black hole. So it's the canonical.
Roughly speaking, the decay time would be exponential of distance to horizon in units of the wavelength?
Well, the decay time is going to be related to the height of this potential barrier. So
tunneling.
Yeah, it's a tunneling thing.
Yeah.
Yeah. So that's why it's slow. So if you look at quasi-normal modes, which were looked at by Festuccia and Liu, they found that if you look at quasi-normal modes with high angular momentum, indeed you see very slow decay. So the rate of decay goes to 0 at large m, angular momentum number. So you see this slow decay in quasi-normal modes.
And how does it go to 0? Exponentially?
Yes, I think it's exponential, but I can't remember the details. And so the behavior of general solutions of the wave equation in this kind of space-time was studied by Holtzagel and Smulevici 8 years ago. And so they proved rigorously that for Kerr ADS and Schwarzschild ADS, the decay of arbitrary solutions of the wave equation in one of these spacetimes is slower than 1 on log t. Okay, so remember in the asymptotically flat case, you have power law decay of massless fields. Here in ADS, you get much, much slower decay. Okay. So remember, if we're interested in the Cauchy horizon instability, that instability is triggered by late time stuff, late time perturbations from outside the black hole.
So this is if you've got some smooth packet in phi. Because you could arrange it to be in a spherical harmonic and then it decays fast.
Any singles, yeah, this refers to a general solution which will involve infinitely many spherical harmonics, yeah. But if you have a bounded spherical harmonic number, then there will be an exponential rate of decay fixed by which one you choose. But for a generic solution, it's like this. So this means that we expect a stronger instability at the Cauchy horizon. Okay, so it's going to be stronger than when lambda is 0. And we know that when lambda is 0, strong cosmic censorship is respected. And so this is why it's generally believed that for negative lambda, strong cosmic censorship is going to be even more respected. Okay, so it's even more likely to be true.
In flat space, the power law decay didn't have anything to do with angular momentum, right? It happened mode by mode.
That's right, yeah.
So
This comes from summing over the angular momentum, yeah. But if you look at an individual mode, you're right, it would decay exponentially. So what we expect is that strong cosmic censorship is respected. Although the mathematicians who are proving things rigorously have only just started working on the negative lambda case. So far there are no rigorous results on this. But what I'm going to talk about,
Cauchy horizon is just a triangle sitting on top of that.
yeah, so this was for Schwarzschild, but if I did, well, I'm going to draw it now actually, but if I do a rotating black hole, there'd be a triangle, yeah.
These boundaries would obviously be the same.
Yeah, the rest will be the same.
So perturbations with the bound on the spherical harmonic, from this point of view, would say are not generic enough.
Yeah, if you put a bound on the spherical harmonic, that's not allowing arbitrary smooth data. So anyway, so this was all for 4 or more dimensions, but there's an exception, which is 3 dimensions. When we have the BTZ black hole. Okay, so for this solution, if we look at the effective potential, it looks like this. Okay, so again, this is the black hole horizon, and you see now the different shape means that there's no stable trap, there's no trapping at all in this case. Okay, so this is for a Schwarzschild, a non-rotating BTZ, but there's not even a photon sphere in this case. So in BTZ, we don't expect this slow decay phenomenon.
And if you added a little mass to that in BTZ, would that change qualitatively?
I'm not sure what you mean by add a little mass. This is massive.
That's massive.
That's the black hole.
No, I mean for the GDC.
Oh, you mean a time like geodesic? Yes, yeah. Well, I haven't thought about how that's going to change.
I mean, it would be surprising if there were no orbits.
It certainly will change. Yeah, I haven't thought about it.
Okay.
But obviously easy to work out. Okay, so let's look at BTZ in more detail. So the metric looks like this. Okay, so again, L here is the ADS length. This is a rotating BTZ black hole. It has an inner horizon and an outer horizon whose radii are R plus and R minus as usual. And this is the ADS length. So if we look at the Penrose diagram, it looks like this. Well, a bit smaller. So this is time like infinity. This is the what I was calling the right component of the event, future horizon, the left component, past event horizon, and then the Cauchy horizon as before. So I'd call that region 1. And that region 2, using the terminology from the previous lectures. So this is R equal to R minus, and that's R equal to R plus. Okay, so the solution can be smoothly extended across the Cauchy horizon in infinitely many different ways. At least if you have matter, it's clear you can extend in infinitely many different ways. In the vacuum case, that's a little bit unclear. So we want to now investigate cosmic censorship here. Is the Cauchy horizon unstable? So we'd like to repeat our scattering calculation. So we'll, again, do the same thing we did before. Just focus on these two regions, which now have a time-like boundary.
Why do you say that the vacuum cases is not working?
Okay, in the vacuum, the problem in 3 dimensions, there's no dynamics for pure gravity, and so it's not entirely clear whether there exist extensions across the Cauchy horizon which are smooth but not analytic in this case. In the high dimensional case, it is clear because the gravitational field has dynamics, but here it's not obvious. But if you just say couple gravity to a scalar field, then the scalar field can become non-zero up here.
So it's very rigid. Yes.
Well, there is no dynamics in the gravitational field. So if there are non-analytic extensions, it's something to do with large diffeomorphisms or something like that. So I don't think anyone's looked at this though. So let's do our scattering calculation again. So we put a wave packet. So this is 1, this is 2, H minus. We'll put a wave packet here, and then we'll also allow for a wave packet coming in from time like infinity. Do the same calculation we did before, so I'm not going to go through the details. It's essentially the same. But the nice thing in this case is we can do everything analytically. All the mode functions are just hypergeometric functions, so you can see all of these analyticity properties I was discussing previously. You can see it all explicitly because it's just hypergeometrics. And what's the conclusion? Well, you repeat the calculation and you discover that strong cosmic censorship, and the decay outside the hole, is determined by quasi-normal modes. Just as in de Sitter. Okay, so we want to know about the quasi-normal modes in this space-time. So let's look at the case of a scalar field with mass parameter mu. Although I'm not going to be using anything from ADS-CFT, it is useful to use some notation from ADS-CFT. So if this is a dual to some operator of dimension delta, then it's convenient to write the mass parameter in terms of delta. And the reason for doing that is that if mu squared is negative, then as I'm sure most people know, there's a choice of boundary conditions. You can either impose Dirichlet or Neumann boundary conditions, and they correspond to different values of delta. So it's convenient to use delta to parameterize the field rather than mu. Okay. So there are two families of quasi-normal modes. So if I write phi is e to the minus I omega t, e to the I m phi times a radial function, then the radial function you can write in terms of hypergeometric functions, and the two families of quasi-normal frequencies can be classified as either prograde or retrograde, and they look like this. Okay, so there's an infinite set of quasi-normal modes. So M here is just this M in the angular part of the quasi-normal mode. Delta is this delta, and P is a new integer which labels an overtone number. So the lowest quasi-normal mode in each family is P equals 0. Okay, these are called prograde because omega has the same sign as M. These are retrograde because omega has the opposite sign of M. So these are in some sense rotating in the same direction as the black hole. These are rotating in the opposite direction. Okay, so this was...
So if you move to analytic omega minus M,
Yeah.
then it's purely imaginary.
Yes, yeah. So
That's
this...
moving it right forward.
Yeah, that's... Okay, yeah, so from the CFT perspective, that's precisely right, yeah. So this was shown by Danny Birmingham a long time ago. If we look at these, we can as we discussed before, strong cosmic censorship is determined by the slowest decaying quasi-normal mode. Which are the slowest decaying? Well, that's very easy to see here, because here we've got R plus plus R minus, here we've got R plus minus R minus. So the imaginary part here is smaller than this, and so the prograde modes decay more slowly than the retrograde modes. So we expect those to be the ones that will be most relevant for the behavior at the Cauchy horizon, and indeed for the decay outside the black hole.
So those are the ones moving the same direction as the
Yeah.
as the black
Yeah.
hole spin.
Yeah. So we would, looking at this, expect on the basis of everything I've told you so far that it's going to be the P equals 0 prograde mode, which we should use when we calculate this parameter beta I defined last time. So the spectral gap, remember the distance to the lowest quasi-normal mode, would be dictated by the P equals 0 mode, prograde mode, and we'd expect that to be the most relevant. However, there's a massive coincidence, a big surprise, which is that if you remember back to lecture 1, we were always interested in the analyticity properties of this thing, which involved these Z, Z tilde, A tilde, and B. So if you remember what these were, so Z tilde, so this is the black hole interior, this is Z. Z tilde was the wave packet on the event horizon, Z was the wave packet along here, and these was A and B were scattering coefficients in the interior. The big surprise is that for BTZ, this scattering coefficient A tilde vanishes at the prograde quasi-normal frequencies. Indeed, exactly, yeah. So this 0 cancels the pole in Z tilde. And that means that, in fact, it's only the retrograde modes that matter for strong cosmic censorship.
So I think the prograde ones are when the particles move in the same direction as the black hole?
Yeah.
So the ones opposite are
Yeah, so most slowly decaying quasi-normal modes have a zero which cancels the poles, so they don't actually affect the smoothness at the Cauchy horizon. Okay, I should emphasize outside the black hole, of course, the prograde modes are the dominant ones, so that they determine the late time behavior of the field. But in the interior, there's this big coincidence that means that, in fact, the prograde modes just cancel out.
What is exactly the meaning of this range?
So we discussed this. So I mean, one way you can think about it is you can define a notion of quasi-normal modes for the black hole interior. So these modes, A tilde vanishing means that these are modes which are smooth here and here. So they're modes which are ingoing here and outgoing here. They're totally reflected in some sense. So the coincidence, if you like, is that this class of quasi-normal frequencies of the black hole exterior coincides with a class of quasi-normal frequencies for the black hole interior. Okay, so it's just a big coincidence that happens for BTZ. So that means that when we look at the smoothness at the Cauchy horizon, we find that the field is CK at the Cauchy horizon, if and only if beta is bigger than K. And when we calculate beta, we should only use the retrograde modes. So if you do the calculation of beta using the, so we're just going to plug the spectral gap coming from the retrograde modes into our definition of beta, using the surface gravity of the Cauchy horizon, the result you get is this. So this is the retrograde spectral gap divided by the surface gravity of the Cauchy horizon. Good. Y minus, because we're using the retrograde. Sorry, this is coming from the surface gravity. Yeah. Okay, surface gravity vanishes when R plus equals R minus.
Oh, the numerator is coming from there.
Yeah, so I haven't told you what kappa minus is. There's a simple, so alpha is R plus R minus over L times delta, and then you divide by kappa minus and you get this. Good. So we can draw some conclusions from this. So the first conclusion.
So the
Yeah.
imaginary part was basically independent of n. Is this right?
That's right. Yeah.
It's totally weird.
Yeah. Yeah.
Independent of n, the angular momentum.
So the first thing we can notice is that the smallest, if we have multiple scalar fields, then the one with the smallest value of delta is the one that's most important. So it gives the least smooth behavior. Second is that for any, looking at this expression, you can see that whatever delta is, if you take the black hole close enough to extremality, if you take R minus close enough to R plus, then beta becomes very large. So you can make beta as large as you like. So for any k, the field is CK at the Cauchy horizon if we're close enough to extremality. Okay. So again, it's a violation of strong cosmic censorship that looks very similar to what we saw for Rice and Nordstrom de Sitter, but it's for completely different reasons. It's because of this massive coincidence that we see for BTZ.
Was that minus in the denominator a consequence of the coincidence or not?
No, the minus here is coming from kappa minus. So the coincidence tells me that when I calculate beta, I need to look at the lowest lying retrograde mode.
But qualitatively, had the coincidence not happened, you would have got a similar result?
I would have got a plus.
You would have got a plus.
Yes.
The minus would cancel with the numerator.
Yes, exactly. Yeah. So the prograde modes had an R plus minus R minus up here, and that would cancel with the corresponding thing in here, and everything would have, well, then I'd have got something which didn't do this. Okay, so this was all for a scalar field, but we also looked at pretty much any other kind of free field you could think of. So the same is true for Chern-Simons, Maxwell fields, Proctor fields, and massive spin 2 fields. And the reason is that all of these fields the equations can be reduced to the equation for a scalar field, it turns out. Okay, so
So I have a question.
yeah.
Even if the coincidence had not happened and you got a plus,
Yeah.
So if you assume that there was, the lowest delta field was a massless field which had delta equal to 2,
Yeah.
you would still have beta equal to 1, and so that would still not be that great. I mean, that
No.
would still be bad for
Yeah, so
consistency,
if the
right?
coincidence had not happened, then from here we would get that beta is less than or equal to delta over 2. So if there were no coincidence.
That's it.
Yeah. So if you want Christodoulou's version of strong cosmic censorship to be true, that would say your CFT has to contain an operator of dimension 1. And that would enforce beta less than a half. Strict inequality. Okay. If you have a massless field, of course, it's not that's not a massless field. But yeah, so that would have been like an appealing thing to be able to say. Strong cosmic censorship makes a prediction about the spectrum of operators in the CFT. But that doesn't happen because that's not what beta is.
Would the conclusion be that there should exist an operator of this kind, a linear operator, if there is a higher one, then that would violate it? Genericity?
Yeah, but the point is they're all there. So I have to include the fields dual to all of the operators. And so the one that's most relevant is the one that's dual to the operator of lowest dimension. Yeah, yeah. So yeah, exactly. For a generic perturbation, I have to turn that on. So yes, so strong cosmic censorship is badly violated. Okay, so yeah.
For very slowly rotating black hole, then SCC can be restored.
If it's very slowly rotating, then R plus and R minus is not close to R plus, and so beta won't be too big. So they might be okay. It's only near extremality that this happens.
And the reason this aided Monica vanishes that type of
The reason,
the tilde vanishes.
Yeah.
That rotate.
well, it's just a coincidence as far as we can tell. I mean, I don't have any deep understanding for why that has to be true. Well, I'm going to explain why now. So let me explain how we can get out of this.
Is the context where the zeros for it will also?
Who was asking the question? Yeah.
Like, is it whether the tilde has zeros?
No. Well, it might do, but they don't coincide with quasi-normal frequencies of the exterior. So.
But there was one argument where you said the poles didn't matter because the z's will develop a zero.
Yeah, so then I was talking about poles in A tilde and B. Now I'm talking about zeros in A tilde and B. Yeah. Yeah. So how can we get out of this? Well, then the simplest way out of this would be to change your boundary conditions. So if we use some non-standard boundary conditions, as I'm sure most of you know, if we have a field with low dimension, then you can impose mixed boundary conditions. So these are the things dual to multi-trace deformations of the CFT. If we change our boundary conditions in the exterior, then that will change the quasi-normal spectrum in the exterior. In the interior, nothing changes, and so we'll destroy this coincidence. Okay, so if we turn on some multi-trace deformation, that will destroy the coincidence, and then we'll be back to what I just said, which is that you just need an operator of dimension 1. Okay, so that's one way out. Another way out is to allow non-smooth initial data, as I discussed last time. Because this just relies on the inequality kappa minus greater than kappa plus, which is true for BTZ. So you can rescue strong cosmic censorship by allowing your initial perturbation not to be smooth, in the same way as for Rice-Nordstrom de Sitter. But if you don't want to do either of these things, then we're stuck with this violation of strong cosmic censorship.
Non-smooth perturbation business, that would also have this curvature similarity.
Well, it depends how non-smooth it is. but we're we're just looking at So have we lost them?
So Shaz, your Skype got disconnected. If you just accept the call, we can start.
Is that okay? Yeah, maybe put the
Mute the microphone.
Skype mic.
Yeah, I muted it, yeah.
Yeah. Okay.
Okay, so what else could we think
So the
of?
weakest version of the censorship
Yeah.
would be that the smoothness always gets worse.
Yes, so it would be the statement. Yeah, so it would be the statement that if you start off with the minimum level of smoothness that you need for the equations of motion to be well posed, then generically at the Cauchy horizon you won't have that minimum level of smoothness.
And that is, this version is true in all contexts.
It's true whenever we have this inequality, kappa minus greater than kappa plus, which seems to be true for all black holes that we've looked at. I don't know why.
And suppose you demand that it's infinitely, your data is infinite, completely analytic. Then will it stay analytic?
Do you mean smooth or do you mean analytic?
I mean,
Infinitely differentiable,
Yeah.
that's smooth.
yes.
No, it won't. It will. So I've been talking throughout about smooth data, and I'm showing that it becomes CK at the Cauchy horizon, where the value of K depends on this beta. Okay, but it's generically it's not smooth there. Yeah. And that's one argument for why maybe you should allow rough initial data, because if you're going to say it's a problem that to have, let's say, C3 at the Cauchy horizon, then surely I should also allow C3 in my initial data, and then if you C3 in the data, it will give it. So that's maybe a symmetrical way.
So there's no way to close the system. Whatever you allow for, it gets worse.
Yes, yes.
But you needed to include infinitely many angular momentum modes, right?
In which case, well, we're talking about. Well, to say it's violated, you're trying to look at. You have to say what class of initial data you're considering. So we want to consider the biggest class possible. So we want to allow all possible.
But that's becoming very wiggly now, right?
Yes, but
if it's smooth enough, meaning that it changes over some range of this thing, then that would put a cutoff on the angular momentum modes, and then you will all.
Well, no, you can write down smooth functions which have support on arbitrarily high values of m.
But also the problem with the BTZ is coming not from large angular.
No.
You're saved in higher dimension
Yeah.
because of large angular.
Yeah.
BTZ, large angular momentum is based on
Yeah, angular momentum's not really doing anything here. It's
No, but I thought there was an issue about the each mode decaying like this thing exponentially, but generically you have 1 over log t.
that was for more than 3 dimensions. Here we're in 3 dimensions. Okay.
Oh, sorry,
Yeah. Okay.
And that's why there was no issue with convex acceleration.
Yeah.
And convex acceleration is obeyed in higher dimensions.
Yeah, that's right. Okay, so let me finish by telling you about another possible way out, or well, another thing you can think of, which is to look at quantum field theory in the BTZ spacetime. Okay, so far everything we've done is classical, but if we form a BTZ black hole by gravitational collapse, for example, it's going to Hawking radiate, and the Hawking radiation will bounce off infinity and hang around outside the black hole. And eventually, the black hole is going to settle down to a state of thermal equilibrium with its own Hawking radiation. So we'd expect the state of a quantum field in the BTZ geometry to approach a state of thermal equilibrium, which is called the Hartle-Hawking state. So at late time, we'd expect a quantum field in the BTZ geometry to settle down to this Hartle-Hawking state. And so how does that help us? Well, in a non-trivial space-time, we have vacuum polarization in the sense that the expectation value of the energy momentum tensor is going to be non-zero. And so maybe this expectation value will diverge at the Cauchy horizon. And perhaps that divergence, when we back react it, will save strong cosmic censorship. And there's some evidence for this by looking at a 2D toy model. So this was done long ago, Birrell and Davis. So if you just look at a toy model for a black hole with a Cauchy horizon in 2 dimensions, and you look at a conformally coupled scalar in this geometry, because you're in 2D, essentially everything's trivial. The stress tensor is just fixed by energy momentum conservation, and you can use that to show that indeed this thing does diverge at a Cauchy horizon. So that is encouraging. So we want to know, does this rescue strong cosmic censorship for BTZ? Or indeed, for Rice-Nordstrom de Sitter.
So is this 2D model something like the mirror space-time that...
No, it's literally you take the Rice-Nordstrom solution and you throw away the sphere, and that gives you a 2D metric, and that's the metric.
Right.
They just study the field in that geometry.
So that I mean, it's the near horizon limit of okay, no,
just throw
the
literally,
full horizon
yeah,
just, throwing away
exactly, yeah.
sphere.
Yeah, it's not, they're not taking a limit, they're just throwing away the sphere.
I see. And therefore, there's no angular momentum.
That's right, yeah.
And they don't even keep the dilator. They don't even keep the size of it.
No, they're not trying to view this as a solution of anything. They're just saying it's at some background that we can study quantum field theory in.
So, another question is this divergence logarithm purely or?
No, I think it's power law if I remember correctly. Yeah. But don't quote me on that. I'm not totally certain. But it's very easy to see. You can do it in a few lines in calculation. Okay, so we want to look at this for BTZ. A nice thing about BTZ is that you can, because it's just a quotient of ADS3, you can calculate everything analytically. So this was first done, so the first calculation of this was done a long time ago by Alan Stife, who was a student of Gary Horowitz, and then a postdoc in Cambridge, and he wrote this, I think, when he was in Cambridge. And what he did is he calculated this expectation value for a conformally coupled scalar but with, from a modern perspective, rather peculiar boundary conditions, the so-called transparent boundary conditions. Okay, so these are the boundary conditions you get by conformally mapping to the Einstein universe and demanding that everything is smooth there. Okay, so that's not the boundary conditions that we would use nowadays. And so anyway, what he found is that this expectation value can be written as an infinite sum. This is basically coming from the fact that ADS is a quotient, so you can use the method of images to construct green functions in ADS, and when you use that to calculate the stress tensor, you end up with an infinite sum.
Once again, a scalar field in ADS.
This is just a conformally coupled scalar field in ADS. Yeah.
He calculated it in ADS3, right?
Yeah. This is this is BTZ. BTZ. Yeah. So it's a sum over a set of terms which are called TABN. These are just, I think they're just polynomials in R. And so since they're polynomials in R, you can evaluate them wherever you want. And what he observed is that the nth term in here diverges at R equal to Rn, which is less than R minus. In other words, it's behind the Cauchy horizon. And furthermore, Rn tends to R minus as n tends to infinity. Okay, so the natural interpretation of this is that this is telling you that this quantity diverges at the Cauchy horizon. However, this is completely wrong. Okay, so this tells us nothing. And actually, Steiff was fairly careful about what he said about this. He literally said these words, and he didn't say, this tells us there's a divergence at the Cauchy horizon. The reason it tells us nothing is that quantum field theory is only well defined in a globally hyperbolic spacetime. In a spacetime which is not globally hyperbolic, it will have all the same problems with predictability that we have in the classical theory, and probably worse. And so, if quantum field theory is not defined in a non-globally hyperbolic spacetime, it's not defined beyond the Cauchy horizon. So this is just some formal calculation. If the field theory is not even defined for r less than r minus, then this is meaningless. So
what happens as you approach the Cauchy horizon?
well, that's the question. Yeah. So QFT isn't defined.
The vacuum state will also be not very different.
Sorry?
The vacuum state will also be
Yeah, nothing is defined. Not defined, not globally hyperbolic. Okay, so
Less than or minus is behind the Cauchy horizon?
yes. So the Cauchy horizon, so the black hole exterior is r greater than r plus. Region 2 is r greater than r minus, but less than r plus, and then r less than r minus is beyond the Cauchy horizon. Okay, so the question, as Abhijit said, is what is the well-defined question? How does this expectation value behave as r tends to r minus from outside? Okay, and if you look at Steiff's result, it actually looks that this is going to be finite near extremality. Okay, and Steiff actually has a little comment in parentheses in his paper where he says this is finite on the Cauchy horizon, but he doesn't explain it anywhere, and all he has is one sentence saying that. So it's a little bit odd. But ever since, any paper that's ever cited his paper has said, and Steiff showed that this diverges on the Cauchy horizon. But he didn't. Okay. We want to repeat this calculation then for more standard boundary conditions and for a scalar field of arbitrary mass. So, how much time have I got? I've got a little bit of time. Okay, so we want to calculate this thing. So how do you calculate this? Well, the first problem is this is a bilinear, or it's quadratic in the field, so when you calculate it, you get divergences which you need to regulate. And this is well understood how to do this in curved space-time. So there's a procedure called Hadamard regularization.
The usual point splitting.
Yes. So let me explain how that works. So the idea is to start from the symmetrized Whiteman function. So this thing is singular. As x prime goes to x. So we regulate the singularity by subtracting something which has the same divergent structure as a quantum field theory in flat space. So we define a regulated two-point function by subtracting this thing h, which is called a Hadamard parametrix, which in full detail looks like this. So this sigma is related to the geodesic distance between x and x prime. So 2 sigma is the geodesic distance squared. And And these coefficients here are fixed by demanding that this thing solves the wave equation, or the Klein-Gordon equation, to all orders in sigma, as we expand this. Actually, yeah.
The principle is that there's some counter term which you found in flat space and then you're evaluating it.
No, the principle is that the divergences in curved space-time are short distance, so they should have the same structure as the divergences in flat space. So in fact, I've written this for Cartle-Hawking. This is actually true for a general state psi.
Right. I don't understand this UN.
So these are determined. So the idea is this is some state-independent thing, which has the same structure as the two-point function of Minkowski space-time. So this thing in particular has to solve the equation of motion with respect to both x and x primed, because the two-point function does. So you determine these coefficients by solving that equation of motion. Okay, so I can tell you what the leading coefficients are when you do that.
So I have a question about this procedure as well.
Yep.
And the question is, so if you just think about the phi OP in curved space, there is of course the identity operator which has the same structure as it does in flat space, because that's just the identity operator. But then we have phi squared and phi del phi, and in principle those coefficients could be whatever they are.
Well, that's right.
So if I subtract those coefficients off.
Well, we're going to calculate phi squared now, so you'll see how this is related to phi squared now. So let me explain how we see phi squared in this picture. So let me just write down what these things are. Actually, I'm not inventing this. This is all standard stuff that's written in textbooks. So if you expand these things in powers of sigma, then this is what they look like. So U0 is 1 at leading order, so 1 over sigma is just the standard divergence you get in flat space. And you see then that's corrected by a term which is the curvature of space-time.
So this operator defined in this manner in flat space evaluates to 0 on the right plane.
Yes. Yeah, and it will be finite for any other state. So given this thing, you can now define, if you want to, you can now define the renormalized value of phi squared by now taking the coincident limit of this thing here.
So it's a generally covariant definition of the operator that has this property of tensor.
It's
your definition, whatever it is generally covariant.
Yeah, so the point is this renormalization scheme obeys a set of axioms which respect general covariance, causality, and various other desirable things that you would like to respect. So that's how you define the renormalized value of phi squared. And then the stress tensor is similarly, we act on this with appropriate derivatives. So there's some operator TAB. If I write down what this thing is.
And presumably the operator definition depends on the fact that it's free.
This is all for, yeah, this is for a free field at the moment. Yeah. Well, I'm only ever going to talk about a free field. So in this thing here, this thing here is just the operator which does parallel transport from x prime to x. Okay, so anyway, so basically you calculate this thing, and then by taking derivatives in an appropriate way and the coincident limit, you can get the stress tensor. So as I just mentioned, this is a prescription for defining renormalized values for quadratic operators. But the prescription can be shown to obey certain axioms such as general covariance and causality and so on. And so there's a theorem due to Wold which shows that if you have any scheme which obeys those axioms, then the results will differ from those of any other scheme which obeys those axioms by something we understand, which is state independent and local. Okay, so the scheme dependence in, we look at this first, is that you can add a linear combination of the Ricci scalar and the mass parameter of the field, and that's it. So these are state-independent constants. So that's the scheme dependence. And similarly, if you look at for the stress tensor, you can add. Well, I'll just tell you the answer for BTZ. There's an answer. So you can add certain conserved tensors which depend only on the local geometry. For BTZ, that means they're just a multiple of the metric.
So I have a question about this as well. So if you look at the Wald scheme, you're right that if you look at two states where the stress tensor differs by a finite amount, this should work. But for example, what prevents me from using the Hartle-Hawken state as a reference state and just declaring that the stress tensor is 0 in that state, and then I compute the stress tensor in any other state that's close to that state by subtracting off the expectation value in the Hartle-Hawken state?
Well, I think.
Why would that be a bad thing? That would also obey Wald's axioms.
I'm not sure that would obey Wald's axioms. I think Wald's axioms refer to being able to define it in a general space-time.
But we're doing quantum field theory about a fixed space-time, so we don't have a sense of the vacuum in some other space-time and then try and compare that with this. So this is the fixed space-time, and why can't we just say the Hartle-Hawken state is a reference state and we compare every state with that?
Yeah, that's an obvious question, but it's wrong. I'm just trying to remember the reason it's wrong, and I can't remember the reason off the top of my head. I mean, you would never see Hawking radiation if you took that approach. Shiraz is shaking his head, so he knows. I can't remember in a short time why it's wrong, but it's something that's discussed, for example, in Wald's book on quantum field theory and curved spacetime. Okay, so. For example, you wouldn't see the fact that the Hartle-Hawking state is thermal, for example, if you did that, because it would just be 0.
I'm not sure actually. I think you probably you'd see some occupation number for these things. The only thing I'm asking is a question about because at the end I know you're going to conclude that for some values of that you're going to find the same range as beta. So you could I think find regularization schemes in which you would find that the Hartle-Hawken state had thermal distributions, but you wouldn't get the same limit on beta that you're finding.
It's true.
I'm just saying that this limited beta that you're finding is
Well, if I do what you said, I'm just going to get 0. I won't find anything interesting, because if I define the Hartle-Hawking state as my vacuum, then this is just going to evaluate to 0. So clearly that won't help me in strong cosmic censorship.
Don't you want a local definition of the operator so that can be used in any space?
Yeah, I think that's the point. Yeah, you want a renormalization scheme that holds for any space-time.
Because otherwise, the reason you want to be able to do it in any space-time is you're interested in how this thing couples to gravity.
Yeah.
So you have to be able to vary the metric.
Good point. Yeah. So ultimately,
if you thought about it from the OP perspective, the bulk OP perspective, not the boundary OP perspective, there is one term which is certainly state independent, which is the coefficient of the identity. So you take the phi OP and you get the identity, and that term is certainly state independent. But then, as Harry just pointed out, you have phi squared and you have phi del phi, and those expectation values could depend on the state.
No.
So if your renormalization scheme involves subtracting off things that are state independent, then that's might be worrying for the.
No, I don't think that involves subtracting of things that are state independent necessarily, but you want to make it make your definition local and in such a way that it will be generally covariant and apply in any space time.
Yeah.
And then it does what it does.
Yeah.
But you don't want to take a reference.
But then there should be a.
Yeah, I mean, but you're part of the part of the motivation for the whole formalism here is that ultimately people wanted to look at the semi-classical Einstein equation where you would back react a quantum field on the geometry. So you need to be able to put your field in a general geometry to do that. So,
Right, but I mean, I was just looking at this paper by Amini and Folaki, which is I think the one you use for the Hadamard renormalization. And for them, the subtractions, not only the leading geodesic subtraction, but even the subsequent subtractions are state independent. I mean, they just write down something by demanding the equations of motion.
Well,
And
yeah,
then
but
it assumes a particular expectation value for phi squared and phi del phi.
they're not just writing that down. I mean, the point is that they weren't the first people to do this. This is a well-established procedure, and they were the point of their paper was they were the first to do it in different dimensions. But I mean, they're just following the prescription that was written down a long time ago in 4 dimensions by various people.
No, I understand. Now, all I'm saying is that it involves positing a specific expectation value for all these other operators that are lower dimension than the stress tensor, which will be more singular in the OPE in the bulk.
Yeah, I'm not sure.
Because, in principle, that expectation value can depend on the state.
Yeah, that's how you should do it, right? You should define a subtracted operator in some local way, and then what? That subtraction evaluates to whatever it evaluates to in your spacetime.
That's right, but you have to do a sieve procedure where you subtract off all the operators of lower dimension than the stress tensor in a systematic manner.
Yes, everything that matters has to be.
And you have. That's right, and in this case, I think because phi has dimension half, it's phi squared and phi del phi, or both, and maybe also phi squared del phi, one more operator. So the operators of dimension 1, 3 by 2, and 2, and so you need to subtract them off. So that, yeah.
But you
So
know,
I just wondered about this scheme, which involves, yeah.
so just one more comment. In a theory that's free, sometimes you can get away with doing sort of very little. For instance, the kind of subtraction we use on the worldsheet and the string. It actually is just the subtraction of the 2-point function with geodesic distance. So I have the feeling that that's roughly what they're doing here.
Yeah, it's just geodesic distance which is defining everything.
But anyway, maybe.
Yeah.
I think I've only got 5 minutes to get to the end of this, so before we get kicked out. So anyway, so this is the method for calculating this. So the point was that this scheme dependence, of course, doesn't affect the issue of whether or not this diverges at the Cauchy horizon, because this is just finite at the Cauchy horizon. Okay, so all right, so we calculate. So this thing, we're getting everything from this symmetrized Weitman function. So use the method of images to get this, and that was done long ago by Ichinosa and Sato. Okay, so I'm not going to write down the expression. So it's a sum over images, similar to what I showed you earlier for Steiff. And what we found is that the limit, as you approach the Cauchy horizon in the Hartle-Hawking state, for this operator is finite. And then if we look at the stress tensor, this turns out to be finite if beta is bigger than 1 and infinite otherwise. This was something we could show analytically. This we needed some numerics. So to do this, basically you have this sum. It's very similar to what I showed you for Steiff. You get a sum of functions of R. You need to show that sum is uniformly convergent. If you have a uniformly convergent series of continuous functions, then it's continuous, and that's how you can establish this result. So it admits a continuous limit to the Cauchy horizon. So in fact, back reaction and vacuum polarization does not save strong cosmic censorship. And in fact, it's interesting that this condition beta bigger than 1 was exactly the same condition for classical perturbations to have a finite energy momentum tensor at the Cauchy horizon. So I have no idea why the same condition is coming out, because we're looking at completely different things. But that's the case. Well, there was some interesting behavior we saw numerically in this case as well, as it diverges, but as you approach the Cauchy horizon, quantities diverge in an oscillatory way. So there's some kind of self-similar behavior occurring as you approach the Cauchy horizon. So this was just something we observed numerically. It oscillates with this self-similar behavior, which we don't understand at all analytically. So it might be interesting to try and understand that. But the conclusion is that strong cosmic censorship is still violated, and back reaction of vacuum polarization doesn't solve the problem. So that's where I'll leave it.
So, how do you define a Hartree-Hawkins vacuum at Cauchy horizon?
Well, the vacuum is defined by analytic continuation from the Euclidean section. So notice I've been quite careful in what I've said. I've never actually evaluated anything on the Cauchy horizon. I've always just taken limits as I approach the Cauchy horizon. Okay. We did look at various other quantities in the quantum field theory. So you can look at, if I go back to the 2-point function and I take derivatives with respect to one of the arguments and then take the coincident limit, we looked at the behavior of that quantity, and we saw that it behaved rather similarly to what we saw in the classical case, in that if you want that quantity to behave, if you take k derivatives and you want that quantity to admit a limit to the Cauchy horizon, you need beta bigger than k. So it looks like, so people doing quantum field theory in curved spacetime talk about Hadamard states. These are the states with the same short distance behavior as in Minkowski space. And so you can talk about the Hadamard condition being satisfied to some order. So in other words, this expansion I wrote down in sigma should capture the local behavior to some order in n. And so what this shows is that the Hadamard condition is violated at the Cauchy horizon at some order, and that order depends on how near extremality you are.
ICTS questions?
Yes, so in your paper you have a comment about smoothness, which is maybe what you said now.
Yeah.
But in general, you don't expect the correlation function of a field to be arbitrarily differentiable, right? I mean, if you had some field of non-integer dimension, you wouldn't expect it to be arbitrarily differentiable. So I was wondering why you...
I'm not sure why you say that.
I mean, you might have just 1 by x minus x prime. You might have 1 by x minus x prime to the power delta if you just take a conformal field theory.
Okay, but that's the divergent thing that I'm regulating. I mean, the question is whether it's smooth after I've regulated it.
Yes, after you regulate it, you still have OP coefficients which will have delta 1 plus delta 2 minus delta 3. And so there will be all these coefficients which would be non-integral, and then, those are the parts that go to 0. They go to 0 as the points become coincident, but they're still, if you differentiate them sufficient number of times, you still get something that's bad.
Well,
I mean almost any CFT would have this.
I mean, that sounds like it differs from what people doing rigorous quantum field theory in curved spacetime using this approach would say, which is that once you've subtracted this Hadamard parametrics, the thing that you're left with should be smooth.
Yeah, I mean, maybe for free field theories in Minkowski space, this is
this is what's concerning me a bit when you keep talking about the OPE. Is it sounds like you've got some interacting theory in mind, but yeah, this is all just free field theory.
Okay. Yeah.
So, big question. What do you think it means?
What do I think it means?
Do you have a fantasy?
No, I mean, the thing I haven't mentioned, so there was this paper by Gary Horowitz and Netta Engelhardt who wanted to propose something they call a no transmission principle, which I mean, I think they were motivated by if you analytically extend beyond the Cauchy horizon, then you get a singularity. But then you can extend into a new region with a new asymptotic infinity. And so they're saying, well, from ADS CFT, we've got a CFT here, and somehow at infinity, this CFT is somehow influencing another CFT up here, and that shouldn't be allowed. And so they said there should be some principle in quantum gravity which forbids that. And then they said, well, look, we've got this strong cosmic censorship which appears to be implementing that principle. I never really understood what the argument was which led them to conjecture this principle, but it seems that strong cosmic censorship is not enforcing it. But it's not clear to me why they want to draw this particular space-time, because as I've emphasized, once you've got a Cauchy horizon, definitely when you've coupled to matter, you could have anything up here. There's all sorts of other kinds of space-time, and it's not clear that they're going to have these other asymptotic regions that they're worrying about.
Because you compute an S matrix in the usual observable zone. But I'm not sure what the question is. But I was wondering whether for exactly this case, because it's an overfold, presumably with
Yes,
calculations.
yes.
I was wondering whether there's something one could calculate that would be.
So you could look at the string propagating at the Cauchy horizon and ask, does it get excited as it crosses the Cauchy horizon? Is that what you mean?
Something like that.
Yeah.
Or
Yeah, my guess is it's not going to see very much there if the Cauchy horizon is very smooth.
yeah.
But actually part of the problem is so I mean calculating string propagation or studying it for exact BTZ would be fine, but you might want to study string propagation in the perturbed BTZ geometry, which has only a finitely differentiable Cauchy horizon.
Now suppose we took the full global geometry for exact BTZ.
Yeah.
Now you as you say, there are time-like trajectories that go from one asymptotic to the other. So that geometry could be set up like a 4-point function calculation where 2 operators are up, 2 operators are down.
Yeah, well, I think you come back to the problem that there's a region where quantum field theory is just not defined. For example, there's this region here in the analytic extension of BTZ with a singularity. So now you have to tell me what boundary conditions you're going to impose here.
Right.
And of course, strong cosmic censorship was invented precisely because we don't know the right boundary conditions at a time like singularity. If we did, we wouldn't care about it.
Just to say, maybe I would actually feel, maybe that the other effects, and maybe that's something that they slow strong cosmic censorship, but if strong cosmic censorship is violated, isn't it a serious problem for, the ADS CFT description? Because you take the eternal BTZ black hole, and that's believed to be exactly due to the entangled state of 2 CFTs.
Yes.
But if strong cosmic censorship is violated, you can have things that just exit the system.
Right.
So, you don't have. So I mean, isn't it? I mean, it clearly suggests that if it is violated, the ADS-CFT description of the system is incomplete. It may not be violated. I would say maybe that there are other effects that come in and save it, but otherwise, I mean, isn't it clear that it suggests there's a problem with the description?
And the problem would be that there are some questions that seem physical that the CFT.
That's right.
That the CFT cannot answer.
That's right. And as we discussed, there are these questions of Poincare recurrence. The CFT tells you have Poincare recurrence. If you have an observer who comes in, the observer has to come out after some time because you have a discrete spectrum on the CFT.
Right.
But in the bulk, it looks like the observer can cross over into this other universe. So what does it mean for the observer to come out?
Right.
Yeah.
So could you make that sharp, Subrat? So can we?
Actually, yeah. Just to say, by the way, there's one more effect. I think if you want to ask about strong cosmic censorship, there's another effect that needs to be taken care of. That's the fact that the violation of strong cosmic censorship relies a lot on the late time decay of initial data outside the horizon. But we know that that's not correct for times of order S and longer. Just because there's a fat tail in the 2-point function which is dictated by unitarity. So the 2-point function saturates at e to the minus s by 2.
But I don't think we understand.
And because cosmic censorship.
Sorry, I was going to say I thought.
Yeah, because cosmic censorship.
No, go ahead.
And because cosmic censorship involves a question about what happens at infinitely late times on the exterior, you might worry about whether these non-perturbative effects restore cosmic censorship.
I thought no one understood these non-perturbative effects properly from a bulk perspective. So I think Maldacena had this proposal, didn't he? I thought there was this proposal Maldacena made that you should somehow superpose bulk geometries, and that would restore unitarity. But then it had been shown that this didn't quite work.
That's right. Yeah. But you do have these e to the minus s by 2 tails, whether you understand them well. I mean, I agree we don't understand them well from a bulk perspective, but you have them, and they will affect the statement, right? Because they are very late time tails.
Yeah.
Right.
Yeah.
Well, there's also the whole thing about firewalls, which I didn't discuss, which again is a late time effect, which
But that's on the outer horizon.
Okay, but if you make a late time adjustment to the outer horizon, then that's going to affect the inner horizon.
Right. But let's suppose firewall.
I think for the eternal black hole, there's no serious claim that there's a firewall. If you just take the eternal BTZ black hole.
No,
So, I don't think even AMPS could claim there's a firewall for the eternal BTZ black hole. I mean, maybe for collapsing black holes or something, but if your story applies also to the eternal BTZ black hole.
yeah, but it will be a bit. Okay, but if it would be a bit strange if this somehow rescued it for a collapsing black hole, which has the same late time structure as an internal black hole.
Yeah.
So could we?
Yeah.
So Subrat, could you this business about
Should we get some coffee?
for the entangled for the thermophiles double? Is there a CFT calculation, no matter how hard, that in principle one could do that would either, that would throw light on this issue?
No, I mean, how about just looking for? I think this is one question actually, which might be most tractable. Looking at the fat tail at late times, at time before S, and trying to understand this e to the minus s by 2 behavior, and seeing if that itself destabilizes the inner horizon. Because it's a very late time behavior, so it's also blue shifted by the same amount. So even though the tail is becoming e to the minus s by 2, there's still a blue shift effect near the inner horizon.
But
I think that might already be a compression, yeah.
But this is an effect you're seeing in the CFT. So how are you going to model it from a bulk perspective? I mean,
it's also an effect in the bulk, right? Because the quasi-normal mode doesn't die off forever. It stops dying off once it becomes size e to the minus s by 2.
Okay, but
and then it develops someday.
Okay, but what equations are you going to write down in the bulk to explain that effect?
Yeah, I don't know.
I mean, I agree. I agree. If you modify the late time behavior in the bulk, it will solve the problem. I mean, you could also solve the problem just by saying, I'm going to turn on a source on the boundary which has power law decay. That would also rescue things.
No, I agree. But this is something which is forced on you by unitarity.
Yeah.
Unitarity forces you to have this e to the minus s by 2 at late times. So it's not something we're doing ad hoc. But I agree, we don't know how to model it in detail.
Are there two-sided correlation functions in your thermophile double that would get significant contributions from near the Cauchy horizon?
Yeah, maybe. Yeah, maybe.
There were these old papers, I'm not sure what their status is, but by Schenker and Mukund and other people, trying to find two-sided correlators that got significant contribution from near the singularity of a Schwarzschild black hole. If there were similar correlators that get significant contribution from near the Cauchy horizon, maybe having or not having strong cosmic censorship violation could violate some field theory theory.
But I think maybe the difficulty is that the strong cosmic censorship doesn't refer just to the black hole itself, but to the perturbed black hole. So you'd have to apply this criterion somehow to a perturbed black hole.
But that could be like looking at a 4-point function.
Okay, yeah.
One wave goes and perturbs and the other wave salutes it.
Yeah. Well, in fact, that was something we speculated about in our paper, is whether you can see anything looking at the 2-point function of the stress tensor. Maybe that would be then looking at the back reaction, a second order quantum field theory effect on the geometry.
Yeah, suppose one could show that that if the horizon remains smooth due to arbitrary perturbations, meaning in a high enough point function, that would give you behavior that couldn't be. Here you would be doing it you're not even worrying about what happens behind the Cauchy horizon.
Yeah.
For the region that you can access, if it would give you behavior that couldn't be, you would know something had to be wrong, right? I mean, before you reached that.
Yeah.
I have to say something like this is unlikely, right? Because you have to go blank length within the Cauchy horizon. So whatever you're doing on the boundary would have to be sensitive to. Because even the people who say strong cosmic censorship holds would argue that it holds once you're very close to the inner horizon. So you would have to find some geodesic that really hugs the inner horizon very closely. So you have to find some universal properties.
Well,
Yeah.
I mean, in the kind of thing that Harvey was doing is a strong, let's say in higher dimensional areas, a strong cosmic censorship holds without any reference to Planck scale, right? Just you develop a in the sense that you develop, as you go arbitrarily near, you get arbitrarily bad behavior.
Well, it's not,
Right, but
it's
that
not
becomes
arbitrary. Well,
significant when
it's
you
quite
go
mild,
inside.
really.
Well, it's quite mild, but it has nothing to do with quantum, nothing to do with
No, no.
Planck scale.
No, but that effect becomes significant to cause a back reaction once you're within Planck scale, right? Because the effect is I mean, it's some effect of an order. It's an order 1 perturbation being blown up by an exponential blue shift, and you can ask when does that become order n squared, and it's when you're within log n of the horizon.
Well, I thought it was an issue like, oh, I see. You're saying that the compression of the energy only happens in a very small region. But wait, where does Planck scale play a role? Does Planck scale play a role here? Yeah, so maybe you could ask. Suppose we have one of your power law decays in flat space. How near do you have to go to the Cauchy horizon before you start seeing that, or let's say you've got one of these exponentials so that the total integrated energy diverges. How near do you have to go before you start seeing a lot of energy?
So I guess it's a question of near in which coordinate.
Proper distance.
Is a Kruskal capital V coordinate,
Yeah,
right? It must be 1 over n in the Kruskal capital V coordinate.
Before you start seeing enough
Because the
energy.
divergence
I see.
the divergence is 1 by V to the power.
Yeah.
So the energy that the infalling observer encounters is 1 by V to some power,
Good.
which difference is beta.
Yeah.
And so it's only when 1 by V becomes a order n that becomes something that kills you. I mean,
Yeah.
that really kills you.
So you're saying that, Subrat, you're saying that Newton's constant times energy sources metric. Right? And then,
That's right, yeah.
therefore the energy has to become like order 1 by Newton's constant. That's what you're saying, right? And that's the units in which we're working at the moment? I thought we were working with such that Newton's constant was outside overall. I mean, suppose we look at overall outside 1 by Newton's constant times square root gr plus scalar field. Then in that, there's no Newton constant in the game.
No.
So the stress tensor is just diverging like 1 by V to some power. So I'm just saying that I'm trying to make 1 by V
Large
become
compared
like
to
n,
1.
so that the integrated energy is in.
Yeah, but
Compared to 1 by 1 is ADS scale.
ADS scale, right, ADS scale. But not some Planck scale.
That's it. No, but 1 by V has to become a order n, right?
Why n?
Because the divergence is 1. Because that's, I mean, I'm assuming that an observer can't survive something of order n. I mean, anything order 1, you believe an observer will be able to survive. I mean,
No, I'm just saying that you could ask when does it become significantly different from the vacuum? Right?
oh, sure. That you could ask. That you could ask much earlier. Yeah. That you could ask much earlier.
Right. So that's the kind of thing you might hope to probe in field theory. Right? You might hope to see
No,
that.
but that's happening even in this situation.
What?
Where you have a strong cosmic censorship violation, it's still becoming significantly different. There's still some blue shift. It's just that it's not becoming divergent. You can integrate the flux.
Right.
You could have a violation where it doesn't diverge. If beta is bigger than 1.
Yeah.
Yeah. Okay. Maybe. So maybe. Yeah.
Well, I mean, maybe the field theory would be able to tell you what is needed, right? Right? If
Maybe. Yeah.
I don't know. Of course, it's just a crazy fan. I have nothing concrete to say. But just that this kind of thing was tried before, right? People looked to try to use two-sided correlators to probe funny regions of space.
Yeah.
Didn't have very great success, I have to say.
Right.
But I thought that this had kind of been superseded by.
Chaos and stuff.
Well, yeah, there was how do you see behind the horizon this it was your work, right? Wasn't it the state-dependent probes and so on? Can any of that be applied?
Yeah, you could do that near the inner horizon. It's interesting. Actually, I think Pushkar is going to give you guys a talk on Monday. I don't know if on some of this, trying to do this near the inner horizon. I don't know if you're there.
I do not.
Yeah, you could try and play the same game near the inner horizon. You could try and ask him. It's interesting actually. It's quite different from the outer horizon.
But even already interesting, right?
Yeah.
Perturbations around the eternal black hole.
Right.
So you can, without creating the second
Right.
side, right? So
Right. Right.
yeah, so right, uh, right. Actually, do you know Subra? These issues about the old paper, Mukund and Shankar. I remember they had to do some analytic
Right.
continuation in order to see the
Yes. Yes.
things.
Yes.
Now, by now we
Yeah.
understand analytic continuation of CFT correlators much better, right? You know, there's all this
Yeah.
constantly analytically continuing them from one sheet to the other.
Mm-hmm.
So I was wondering whether,
Yeah.
you know, and that's just often some different ordering of the operators or something like that. So I was wondering whether there's a more modern view on that old paper. Have you thought about it? Or?
Yeah. I don't know actually. No, I have not thought about this. Yeah. This.
Yeah, I mean, it seems to me, even that old question, which never went anywhere because there was some statement and then nothing more you could do with it. But just, what is the signature in the field theory
Yeah.
of having a singularity?
Yeah.
This remains an interesting question.
Yeah.
Have you thought about this, Sundar?
Yeah, it's a good question actually. I've thought about it, but I don't have a good answer to it. I mean, as you say, there is older papers by Mukund and so on, and maybe that's the right thing to look at. But I don't have a good.
It may be worth
It seems to be a much harder question. Yeah. Yeah.
They were looking at 2-point functions, presumably.
They were written at 2.5.
But I think it would have to be higher point functions
Yes.
here. Yeah.
Yes. Yes. No, I mean, you know, there are two questions. There's one question of, can you make an observable that is useful enough to do something with,
Yeah.
which is what we'd ideally want.
Yeah.
But there's a zeroth order question,
Yeah.
which is, can you first find an observable that is sensitive to the issue?
How hard would it be to calculate a 4-point function in BTZ?
Not very hard. Because it's all, and I mean, it's just overfold techniques, right?
Yeah.
Not very hard at all.
Yeah. Well, that's an obvious thing to try then.
Yeah.
Yeah.
You know, of course you could just try. I mean, I have a feeling that if you did the most obvious thing, which is you wrote the correlators in the bulk in terms of the boundary correlators by analytically continuing, which everyone would agree is probably valid for the eternal black hole.
Right.
And then you could try and make the inside point approach the inner horizon. But I have a feeling that would be too close to the bulk calculation. You get exactly what Harvey got by doing this bulk 2-point function.
No,
Yeah,
what about
It would be a prediction about.
you're doing a calculation on the boundary, I suppose, right? 4-point functions on the boundary.
Yeah, you're doing a calculation of boundary, but you map all bulk correlators to boundary correlators, and and that will involve some analytically continued correlation functions because you have some left-right correlators, which you can think of as analytically continued correlators on the right-hand side. And then you could try and ask how that behaves as you approach the inner horizon. I think it wouldn't give you anything very new apart from the bulk calculation. Maybe it would. I mean, these things kind of turn out to be depend on very general properties. For example, this paper that it's a different question. And Kyriakos and Jan de Boer and so on wrote. There's this question about traversability. You can try and they reduce that to some question about the traversability of the eternal black hole. They reduce that to some question about CFT correlators, but it's just a question about whether something obeys ETH or not. It doesn't. It turns out to be often something very, very general, but.
Right.
I don't have anything more useful to say. Yeah,
But just one other vague comment. There are all these sort of papers by Jared Kaplan and company, talking about how if you do just in field theory some vacuum lock calculations, they give you behaviors that are not exactly right. For instance, like your decay, right? They give you behavior that such that 2-point functions just decay indefinitely.
Mm-hmm.
They constantly.
Right.
And they know that if you include in the real theory that doesn't happen. So it perhaps could have that kind of flavor. Some sort of behavior that
that might be nice, especially if one tried to ask about this late time behavior. I mean, Javier was asking what are the equations you would write to model this late time behavior.
Yeah.
It might be, maybe you could, that might be one thing, this late time behavior you could certainly analyze, which these people have done in ADS3 to some extent. Also Sonner and Hartman and so on. So you could try and analyze this late time behavior and using those kinds of questions. And maybe you could relate it to something behind the horizon.
right. Yeah, so maybe the other contributions that would give you the right late time behavior effectively.
I think anything that makes even the tiniest perturbation to the rate of decay at late time is going to solve the problem, because it was really an exact coincidence between the prograde quasi-normal frequencies and the interior quasi-normal frequencies that caused the problem. So if you make a tiny perturbation to the prograde quasi-normal frequency, then the problem is gone.
Right.
So anything should do the job.
Right, but you know, the behaviors, the corrections are so small
Right.
that it's probably not valid to think of these as perturbations in a BTZ black hole.
Yeah.
It's a more.
I see. So, let me ask another question. What if you just turn on interactions in leading order? Do we know if, I mean, that would also modify these frequencies. So do you know if these coincidences persist if you just turn on interactions?
So this would
When
be
you
like
free field limit?
1/n corrections to the.
That's right. Just make the scalar field interact.
I'm not sure that the notion of quasi-normal modes even makes sense when we go beyond the free theory.
Yeah, so I mean, naively it doesn't matter, because you're looking at just the quadratic part.
Yeah.
You know, the idea is that these things decay. Because they decay at late times, the amplitudes are getting very small. And because the amplitudes are getting small interactions.
No, but the rate of decay will get changed a little bit, might get altered in the presence of interactions, so, because maybe things will bounce about a little differently.
I think the
saying the rate of decay gets, yeah.
I think the amplitude will change, but I don't think the rate will change.
Yeah, late enough times it will be free.
Yeah.
And you're worried about late enough times.
Mm.
It's like scattering, right? Scattering is at infinity is free. Doesn't matter how interactive the particles are.
Yeah. Yeah. But what do you think about just deforming the boundary conditions? That solves the problem. An infinitesimal perturbation to the boundary conditions.
You know, we're quite happy to deal with field theories.
You turn on a tiny.
We're not allowed. We don't do genericity on the space.
A tiny multi-trace deformation. Well, maybe this is telling us this theory.
Also for ADS CFT, it's the Dirichlet boundary conditions that are most relevant, right? You take the CFT, you start it in a given state, and then you don't touch it. You just let it evolve unitarily. And so it shouldn't. I mean, you shouldn't have to perturb something with sources. It can also
I'm not talking about sources.
Yeah.
Sorry, I'm not talking about sources. I'm talking about the multi-trace deformation of the CFT.
Yeah, so that would be a source. You turn on the
Well,
source.
okay, there are different kinds of source. There's a time-independent source, like, or you could send in a wave packet.
The CFT.
Yeah, I want to change the CFT rather than turning on a source in a fixed CFT.
Oh, you could turn on, change the CFT.
Yeah.
I think Harvey has in mind that if you're working generically on the space of CFT.
Exactly. Yes.
You won't have a problem.
Yeah.
That's
So
not how we think.
yeah. So exactly. We should add an extra genericity statement.
That might be okay, right? That might be the statement that you shouldn't be at this because there's some moduli space you believe in this in ADS3 CFT2, and maybe you shouldn't be exactly the supergravity point in the moduli space. Is that?
No.
There's some big moduli space in the.
You shouldn't be exactly.
Deforming the CFT in the moduli operator.
You shouldn't exactly be on the D1, D5 CFT, for example. You should deform it very tiny by a very tiny multi-trace deformation.
That's right.
Yeah.
That's right. So maybe this is the same statement.
Yeah.
Right? You shouldn't be exactly at this point.
Yeah. But that seems unsatisfactory. You have to go to a more complicated CFT.
Well, but the D1, D5 CFT has the same singularity. If you look at you have these, you have these long string singularities and so on. So maybe you could have, I don't know. It could be that there's, you have to turn on some moduli. Do I understand correctly that you're saying that turning on the moduli would resolve the problem? That would be a deformation by a marginal operator of the kind you mentioned.
Well, that would in the bulk be saying that small alpha prime corrections or something like that would solve the problem.
Is that the same
No,
thing?
small fluxes.
Small
fluxes would, yeah.
Right. But that won't solve as long as there's no alpha prime correction. For Harvey, the consistent truncation, all he needs is consistent truncation to ADS3 times scalar. So if there's no alpha prime correction, it doesn't solve it. And actually many of his calculations were so robust, right? I mean, his quasi-normal mode calculations you can do in the conformal field theory side, more or less.
Yeah.
Right? I mean,
Right.
it just doesn't have that feel that.
Maybe if we had some understanding of what these interior quasi-normal frequencies correspond to, that might help, because it's that coincidence between the interior and the exterior modes that's causing the problem here. So if we knew what that corresponded to in field theory, but again, it's difficult.
But just to say, that is not very late time, so that's finite time propagation. So that is something that might be affected by interactions. The interior to the exterior, because that's not free field propagation in any
well,
sense.
it depends.
Right? That's actually propagation.
It depends what you mean by time in the interior. I mean, in some sense, R star is an actual time coordinate in the interior, and then it is infinity to infinity. But I'm not sure that's the right way of looking at it.
Yeah. The amplitudes are not becoming arbitrarily small at late times in the early times in the interior.
No, I think that the problem is that if you're going to make any modification to the interior, we did think about this. So you can destroy the coincidence if you deform the interior geometry a bit. The problem is that you have to make a deformation that would be non-trivial here, which is where all the action is happening. The behaviour of the interior just here is essentially dictated by the behaviour of the exterior here, which is just BTZ. So it's very hard to make any kind of a deformation here, which is consistent with the fact that things are settling down to BTZ in the exterior. So so in that sense, there is some kind of decay going on. There's decay as you approach this point here.
Subra, getting back to something you suggested, you were trying to construct the bulk operators. Now, I don't know if you remember, but when Jared Kaplan came and visited both us and you guys, in his last lecture, he did try to construct bulk operators using this method. Nothing very good happened. But just to point that out, that was one of the things he tried to do. He tried to use these boundary correlators to construct bulk operators, and of course, when you used, and in some approximation, they all looked good. But when he went beyond that approximation, he couldn't get anything like approximate locality and so on.
I mean, they have these total field operators.
Maybe that's what I think. There are some operators that behave causally, that commute with each other across, away from, at space-like separation in the bulk in some approximation, and then stop doing it in some other approximation.
Yeah, but they're proto-fields. So you could ask if the real field in the bulk is a sum of many of these operators that they constructed. Basically what they got right was the gauge constraint, because you're always worried about the fact that you have some Wilson line going from the boundary to the bulk. So the thing that they really got right was that. But then you can, the fact that the real bulk operator might be one of their operators plus the double trace proto-field plus something else that they haven't accounted for at all. So but maybe you could do something more sophisticated to make it work.
Yeah, I mean, BTZ is great because the field theory is so easy, right?
Yeah.
So somehow you should be able to use that to clean it up, I think. I mean, it's great you have your violation in this simplest of systems.
Yeah.
So can I ask one more question about this thing you said, late times? One thing you would always worry about is if you have an observer who really tries to cross the inner horizon, that observer, just by virtue of being present, perturbs the geometry.
Yeah.
And so you might have worried that the back reaction would somehow destroy the coincidence. So that would be something that would, again, I'm going back to this question of non-linearity.
Well, I mean, an observer.
Did you just say that's an argument important?
You mean if you do an observer like that? Is that what you're thinking of?
Right, you do an observer tries to cross?
Yeah,
and the observer would himself back react to the geometry.
Yeah, but locally that observer's not going to be blue shifted when they cross the horizon. There's just going to be some finite amount of energy crossing there. What will be blue shifted is the gravitational radiation this observer emits, which then falls in at very late time. Okay, but the observer themselves, they just have some finite energy as they're not being blue shifted.
That's right, but they would modify the interior geometry by virtue of passing through it, and I'm wondering if that would affect the blue shift of their own gravitational radiation and somehow lead to some
think it just comes back to this issue that really all I'm ever interested in is a neighbourhood of this point here, and in this point things are settling down at late time, so the geometry is not affected. It's just determined by whatever the bulk geometry is settling down to.
I see. So, and can one do the analog of the Stanford-Shankar calculation? I mean, that's related to that, where you send in something at very late time from the outside, and you have some other shock wave that comes in at early times, and they collide, but not near the outer horizon, they collide near the inner horizon. That's how I was thinking of modeling this observer interacting with his own gravitational radiation that he emitted a long time back.
So you want
That's a doable calculation problem?
you want the shock wave to describe the observer's radiation. You want, see what I
That's right. That's right.
That's
right. That's right.
Yeah, I guess you could do that, but then I mean it's not going to tell you anything interesting unless you then take the limit where this shock wave goes to infinity.
I suspect that shock wave would completely destroy the geometry. The naive, naively would assume that it would destroy the geometry.
Well, I think it's going to be.
Because
I think it will be delicate because the shock wave itself is already a singular thing. So how are you going to distinguish this singular thing from an actual physical singularity on the Cauchy horizon? You have to somehow,
I mean, you do it before the Cauchy horizon, of course. You have the collision just outside the Cauchy horizon. I don't know if that, I'm just thinking there's an invariant boost between the observer and his own radiation, which is large.
Mm-hmm.
And that might,
Yeah, well, I agree. It will become large in the limit, but I'm not sure you need the observer then. The radiation alone will do the job because it's already blue shifted. But I guess we know that's not strong enough from the calculations we've done.
Right. That's why I was trying to put in both these people and make them collide with the radiation and the observer.
Yeah, I guess I shouldn't have mentioned gravitational radiation either because there is no gravitational radiation in ADS3. So, some other kind of radiation that scalar field radiation.
Scalar radiation. Yeah.
Good.
Okay, maybe we can let Harvey go.
Thank you.
Thank you very much. Thanks for sitting in on the lectures.